I just want to know, why is it whenever you're running late, that's when you hit every friggin' red light? It drives me insane. Every single one on the way here. I was cutting it close as it was, and then the red lights got me. But anybody have questions before we get into this? Okay. Let's do this thing. Okay, so today we're talking about immutability. We've seen some of the effects of immutability throughout the semester, just the way certain classes, certain types work, specifically strings and lists. And so far we've just said these kind of behave like they're on the stack, and whenever you make a change, whatever you call a method on these things, add to a list, change a string in any way, concatenate strings, we always have to reassign that back to our variable. So I want to talk about that, why we have that behavior, when we should expect it, when we should not expect it, and how these really work in a lot more detail than just, they kind of act like they're on the stack. So to that end, the lecture question today is to write a point class that has two values that it takes in its constructor using the keyword values, so these cannot change. We have an immutable point, a point that once we create it, once we call the constructor with an x and a y, we cannot alter x or y at all. We have two methods, add and multiply by scalar. Add, where we're adding 2 points together. Think of these as kind of vectors, vector math. Adding 2 points together, you're going to add the x and y component-wise. But since x and y cannot change, we're not actually adding 1 point to the other point, but we're going to return a brand new point with those x and y added to each other. This is how we get our immutability. Since the point cannot change, we're going to simulate changes by returning a new object of that type with the change reflected in that new object. Same thing with multiply by scalar. This takes one double, and we want to return a new point with that double multiplied by each component to be able to get the new point with that scalar multiplied to it. And then our test suite, how do we test this? Getting that behavior, making sure that we are immutable and get that immutable behavior out of our point class by taking the references to the new points that are returned and checking those references for the proper values. X and Y are named here, so you can access these. They are vals, so they're accessible. So you can use X and Y in your testing. And just one word of caution here, since we are using a class named point, there are a lot of other classes named point in the standard library. So when you import the point class in your testing, make sure you're importing functions.point. Don't import one of the other ones. This is actually why, if you're wondering why our class in the physics engine is called physics vector and not just vector, because physics vector doesn't clash with anything in the standard library. But at this point in the course, I want to start focusing on other aspects of programming, and that's one of them. We can have these classes with different names, or the same name, as long as they're in different packages. But at physics engine, the first homework assignment, I don't want people getting tripped up on that. So I call it physics vector instead of vector. If you're ever wondering why I call that physics vector, that's why. There is a vector class in the standard library. And I've seen that before. There's nothing worse. The first few weeks is already stressful enough. Seeing a student who has the wrong vector imported, that's not something that's fun for anybody. So we avoid that early on. At this point in the course, no pun intended there, we can use the we can use the duplicate names and make sure that we have the proper imports there. Okay, immutable objects. The values cannot change. Once the state is established, we have that initial state either in the constructor or just some default state that cannot ever change. That state is not changing. The state variables never change in an immutable object. So the big question is, how do we work with these? What if we have an object that naturally has a changing state, like a list, like a string, things that we want to modify, or the point class for the lecture question, these things that we don't want just one value that never changes. We might have a point that represents the location of an object that's moving around. How do we do that with immutability? And we're going to simulate the changes by returning a brand new object that's a copy of the object that we're working with the changes reflected, create that new object, and then return a reference to that new object. And this is how we get all the advantages of immutability, but still be able to kind of simulate a changing state. We're going to do that by always creating a brand new object. So let's look at an example of this. I have very simple, very artificial, academic kind of class here. A mutable counter which initializes a counter to some value through its constructor, and then that value can never be accessed again and can never be changed. We don't have val or var. We can't access this variable from outside of the class, but we want to be able to know what the counter is. I have this kind of artificial print counter method just so we can see what that value is. Missing one space there. Oh well. Just so we can see what the value of that counter is, but I want to lock this down to make it so we can't access it from outside the class. I'm doing that specifically just so we can force recursion on this as well. And we also have two methods. The only ways that we can actually change the counter is by calling either increase, which is going to add 1 to the counter, or decrease, which is going to decrease the counter by 1. And each of these methods, since we can't just say counter plus equals 1, counter minus equals 1, we can't do that. Counter can't change because I didn't use var. Counter can't change, so I'm going to return a new instance of the immutable counter class, a new object of type immutable counter with that change reflected. The only way I can change a counter, I can't change it, but the only way I can get an object with a different counter value is by creating a new object and giving it that new value in its constructor. So that's what I'm going to do here. I'm going to say this.counter plus 1 and create a new immutable counter object with that updated value. I got ahead of my slides, but and each time we call increase or decrease, we're actually creating a new object, putting that new object on the heap, and then returning a reference to that new object. It's really a feature of these immutable objects, these immutable classes, is we're going to create extra copies of them, put those copies on the heap, and then return references to those copies whenever we want to simulate a change. It's going to be a theme throughout today's whole lecture, is that change, or is that way of doing things. So now if we want to actually update the counter, what we could do is use var and use a loop. If we say want to add 10 to the counter or add some variable number to the counter, what we can do is create a variable that stores a counter, a variable of type counter, create the counter, have that variable store that counter, and then loop 10 times. Say for I in 0 until 10, my counter variable equals that counter variable dot increase. And then create a new object on the heap 10 times, create the new object, reassign that object to my variable, and then on the next iteration of the loop, on that new object, we're going to call increase, create a new object and reassign that to my variable, get the next iteration of the loop on that new object that was just created, call dot increase again, get a new object on the heap, and return a reference and reassign that variable to that new reference, and keep doing that throughout the entire loop. That's how we would do it if we're using mutable state, if we're using variables. The functional programming way of doing this is what's on the screen. The recursive way of doing it is if we want to increase a counter by some value, I'm going to call this update counter method, which is going to take an int, the number that I want to change the counter by, and a reference to a counter. I'm going to get those values in update counter. My base case is going to be 0. If n is 0, you don't want any change to this counter, so there's no work to do. We're not going to do anything. We're just going to return whatever counter you gave me. You gave me a counter, you told me to change it by n is 0, you must just want the counter back. So I'm just going to give you back that counter. If n is not 0, whether it's negative or positive, I'm going to modify n by 1. I'm going to get it 1 closer to 0 and call either increase or decrease depending on which direction I'm moving in. So each time we hit one of the recursive steps, we're going to call increase or decrease, which is going to create a brand new immutable counter. And I'm going to return that new immutable, I'm going to use that new immutable counter in the call to the next iteration of update counter, not iteration, but the next recursion of update counter. So I'm getting the same behavior as the loop, but I'm creating a lot of values on the stack as the stack grows for each call, instead of iterating through a loop and reassigning to a variable. I get the same effect, but this is the functional way of thinking, the recursive way of thinking, instead of the iterative way of thinking. But we can get the same thing done using the same kind of thought process, but a different approach to be able to accomplish the same task using the recursive method instead of the iterative way of thinking. So we have a completely immutable object, and we have complete immutability throughout our entire program. But we can still get the same things done. If we want functionality, we want a counter that's either counting up or counting down. We want to adjust some value of a state variable in an object. But we can't have any mutability anywhere in our program. Maybe we want to have this running in a data center somewhere, spread across a whole bunch of servers. Hopefully not just to compute this, but doing something more complex. We can still get that stuff done by using our functional approaches. With that recursion, we never updated a variable, we never changed a reference, but we still got the same thing done. All right. Any questions on this example? So this is showing how we can build an immutable object by returning new instances of that type with any change reflected if we want to simulate a changing state. And then sometimes we do have to use recursion, plus honestly I just wanted another example of recursion in here. You can never get too many examples of recursion. I'm going to show recursion until it starts making sense if it isn't already. So we can use recursion to be able to get the same things done without having that mutable state. So if we do need immutability in our programs for our architecture, we can still get the same things done that we could before. We just have to set them up a little bit differently. Strings are immutable. So strings do this. I shouldn't say all, but any string method that seems like it's changing the string is actually returning a brand new string with that change reflected. This is how strings work, at the very least in Scala, but in a lot of languages, this is how strings work. Strings are immutable. So let's look at an example. We're going to bring back the old stack and heap. And again, you can count on this for lab when we come back. When we come back from break, well, if we come back from break, I guess, that you can count on stack and heap diagrams coming back. Whenever it does end up happening that next lab, you can count on stack and heap questions. So let's step through a program and talk about the stack and heap and how the stack and heap update when we're working with strings. All right. So I didn't start right at the first line. I'm skipping some of the steps that are just tracing through stack and heap. I'm assuming we're good with that stuff. But let me talk through what did happen so far in the execution of this. I started main. I created a value named course. Created a new string. We have this shorthand syntax where this looks like a string literal. This is the same thing as saying new string and creating a new object. We are creating a new string object when we use this string literal syntax. This creates a string object It goes on the heap, it gets a reference, it gets memory allocated to it, and we have the value of that string stored on the heap, and then we get a reference to that object on the heap. I'm going to keep my numbering simple. I'm just going to start with 1 and then increment instead of coming up with random numbers each time. I'm just going to use them sequentially starting at 1. So I have this space on the heap. I'm going to store CSC 116 in a string on the heap and get a reference to that. And I'm going to say that reference was at 1. Store that in this variable course. Call this method nerf. Give it that input, which is the reference at 1. Input is that reference 1, referring to this string. And then we finally get to the point where we're doing some stuff. We want to call dot replace. I assume by this point, most of you know that if you call dot replace, you have to reassign that back to the variable. Usually you would do something like course equals course dot replace 6.5. You would do something like that. You would reassign that back to your variable to be able to get that change reflected. And we kind of hammer that into your heads, like you just have to do that. But now I want to explain why you have to do that. Why are we doing that? Why are we reassigning this back to the variable instead of just calling dot replace? It seems like dot replace should go into the state variables and modify them. But as we're seeing now, of course, since the string is immutable, we can't actually modify this string. We can never change this value. This is always going to be on the heap as is, and we cannot change a single character of that string. It is immutable. We cannot make a single change to it. So when we call input.replace, what we actually get is a brand new string created, added to the heap. We ask our operating system, we ask the JVM, we say, we need some space on the heap. We need enough space to store this string, CC 115. We get that space, we store that string, we get a reference to what we stored, and we actually get this reference at 2, which is the return value of the replace method call. So when I call .replace, this is returning a reference to the brand new string that was created after the replace method found my string 116, made that change, but didn't actually change anything, but created a brand new string with that change reflected and returned a reference to that brand new string. So this resolves to some new reference to a new string with the change reflected. And here, we're not doing anything with that string. We're returning unit. So we're not actually returning anything. We don't do anything with that reference at 2. So we created this brand new string on the heap. We didn't do anything with it. We don't actually see any change in our program because we never did anything with that new reference that we created, the reference to the new string that we created. So now this reference is the string. It's still on the heap, but we just can't do anything with it because we never assigned that reference to anything. We didn't return that reference. We didn't do anything with it. We just leave it on the ground, or rather we leave it in the heap, and we lose that reference to that string. So in our main method, and when we look at the stack is in the same exact state as it was before that method call. That method call had no change on our actual program itself. All it did was change heap space a little bit, and not really a topic I'm going to talk about too much, but that reference, this string, is actually could actually get garbage collected. We no longer have any references to it, and what Scala does, what the JVM does actually, is looks through everything on the heap and looks at our code, our program as it's running. If we don't have any references, if we have no control of any references to that object on the heap, the JVM is going to do what's called garbage collection and get rid of that, free up that space, and give that space to some other program or give it back to the OS or do whatever it's going to do with it. It's going to take that memory away from us. This is what's avoiding memory leaks when we create tons and tons of objects on in the heap, but we don't actually do anything with them. The JVM is going to come through and garbage collect all that stuff for us and clean it up. We're not going to talk about that too much in this class. It doesn't affect our programming too much. Suffice to know that garbage collection is a wonderful thing, and it's an absolutely great thing to have. Python had it, JavaScript had it. You never had to worry about this memory management thing, but as all things, 220, you will worry about that. You're going to use C, which does not have garbage collection, and you will very much so have to worry about this, which is what that course, a big part of what that course is teaching you, is how to manage your own memory. When you have things on the stack, you have things on the heap. You'll actually ask the OS for your own heap space, and you'll manage your own heap memory. So don't think that stack and heap are going away. I'm just laying the foundation that they're going to build on in 220. So just a heads up about that. Right now we have garbage collection. 220 is going to say, what if we didn't? What if we didn't have garbage collection? And then what do we do with that? How do we manage that memory? How do we become space efficient? How do we avoid memory leaks and things like that? So just a heads up on what that class is about. I talk about 250 a decent amount, but I don't talk about 220 as much as I could, but this is one of the 220 things. What happens when garbage collection goes away? All right, enough advertising. The next thing our main method does, our program does, gets this next line and calls another method. This one is actually going to return a string, and we are actually going to assign it to a variable. So we actually get some action going on here. We're going to call this amplify method. We're going to pass it that reference at 1, the only reference we actually have access to. Course is a reference at 1. We're going to call it with course. So input is going to get that reference at 1, which is this string cc116. We're going to call replace. Replace is going to do the same thing that it did in that first method call. It's going to create a brand new string on the heap, in heap space. That string is going to have that change reflected. So input, we're going to at 1. We're going to at 1, looking at this string and calling replace 116, 250 on this string, finding the substring 116, replacing that with 250 in a brand new string without changing this string. Nothing on the heap is going to change throughout this entire program. Nothing changes, we're just adding more things to the heap. This doesn't change, we return that new reference at 3, and this input.replace resolves to at 3. That's the last expression of the method. It returns string, not unit, so we are actually going to return this at 3. And then we're going to store that at 3 in a new value named data structures. So now in the main frame, we have this new variable named data structures. It stores the reference at 3, which is a reference to this string, which is the string 250. So now I have a new reference with a new value with a new reference with that change reflected, and I have access to it in my main method. Even though it was created in a method call, it was able to return that reference and get that reference like we've seen before. We've seen references passed around. We just haven't seen it with immutable objects. Next, we get to the next line. We can see these changes even if we're not calling methods. We called a few methods already. But even if it's just in the main method itself. If we have string concatenation, it's another method call. Even if this were an operator, we could talk about the subtle differences. Even if it were, strings are immutable, so we can't change a string regardless. So we have something that's going to give us this new string, but we can't go to course, which is at 1 still. Of course, that can't change either because it's a value. Going here, looking at this string, and then concatenating another string to it. Actually, I missed something here. This string literal is great. That would have to be another string on the heap as well. We would actually have another string. I'll add that. Is great. That's going to be added to the heap as well. We have these two strings that are going to be concatenated. We're going to get this new string. CSE116 is great, a very true statement. That's at some new reference, but I never reassign this to anything. I never assign this to any value or variable. So I just lose that change. That string was created. There was a string concatenation which created another string. A lot of action happened there, But since I never stored that returned reference, this is going to resolve to the reference at 4. Since I never did anything with that reference, I don't get to see any of those changes. This is one of the mistakes I think everybody makes in 115 before we really get this in your heads, that you have to reassign this to the variable where it came from. You would have to do course equals, course plus is great. You'd have to do something like that to be able to see that change. And now we can finally see why. This is going to create a brand new immutable string, resolve to a reference to that string. Then we have to do something with that new reference, because the original string remains unchanged. It's immutable. It's never, ever, ever, ever going to change. The only thing we can do is create a variable, which we would normally do, create a variable here, and then reassign the reference. Instead of course referring to 1, we would want course to refer to 4 now, to this new string that we created. That's the typical way that we would use this. That's typically how we work with strings, is reassign the reference, the new reference, to our variable, and update that reference to the new string. And then is fun, space is fun, would also be another string that's created, put on the heap. Then we're going to concatenate. This time we are doing what we're supposed to. We're going to reassign this to a new value. And now course string is going to get this reference assigned to it. And we're going to have course string with that reference at 5. And now we can see that change reflected in this new value named course string. Then we would get what we expect. Course, we can follow the stack and heap diagram. Course at 1, we're going to print CSC 116. Data structures at 3, we're going to print 250. Course string at 5, we're going to print CSC 116 is fun, to get that behavior out of there. All right, any questions on this example?
Someone Chris asks, can we go back to the second RAM and change it after we do the fourth RAM?
Can we go back to the second RAM? Can we go back to our second RAM after we got the fourth RAM and use our second RAM? Not anymore. So we don't have access to @2. We don't have that stored in a variable anywhere. We don't have that reference in a value or a variable or as a parameter. Since we don't have that reference anywhere, we actually lose this completely. We can't access this string anymore, and we can't access this string anymore. Once this one was created right here, since we don't do anything with the reference, we have no way of accessing it ever again. We completely lose that. And that's where the garbage collection can come in. Since we have no reference to it, we can't ask the heap, hey, what's all the stuff that you have? Let me check it out. We can't do that. We can only access things on the heap if we have a reference to that object on the heap. So if we don't have any references to it, we cannot access it. We lose access to that object. And that's why garbage collection works. Garbage collection says, you don't have any references to this. If I delete it, there's no worries because you literally can't access this anymore. So you're not even going to notice the garbage collection coming in because you cannot access that anymore. If we could access it, if we could ask the heap for all of its objects, garbage collection wouldn't be able to exist because it would never be able to delete anything because it doesn't know if you're ever going to access that again. But since you can't access 2 and 4, those are going to be garbage collected. And those strings is great and is fun that were created. Those could also be garbage collected because we don't have access to them anymore. Any other questions on this example? If we store those references and variables, we can't go back. Once we have this reference, we create the string and get that reference, and we move on to the next line without doing anything with that reference, we lose that reference forever. We cannot reclaim that reference. Once we move down with our program, we've left that reference on the ground, we walked away from it, it's never coming back. No way of accessing RAM at 4 anymore. Lists are immutable. I've mentioned this throughout the course, lists and strings. These are two of our big immutable things that we're using. So let's take a look at some lists. And hell yeah, I snuck in some more recursion in here. So let's take a look at some recursion with lists and trace through this thing to see how we're going to compute the first n primes. For this example, I'm just going to compute the first 3. So let's compute the first 3 primes. Just a quick overview of my program itself before we start talking about stack and heap. I have this recursive call to find the top n primes. It's going to return a list with all those primes. If n is less than 1, so if you want 0 or a negative number of primes, I'm going to return empty list. I'm going to say, what are you even doing calling my method like this? That's silly. Here's an empty list. If n is 1, I just want the very first prime. This is my more meaningful base case. That first base case is more error handling. If somebody misuses this method, this is what I'm going to do. My actual base case is n equals 1. If you want the first prime, that's 2. And that's going to seed everything to be able to start, get the ball rolling and start my computation. So 2, that's the first prime. Else I'm hitting my recursive case. I'm going to get the first n minus 1 prime, so my recursive call is getting closer to my base case, so I'm good on that. And then I'm going to write the rest of my logic just assuming that that does return the first n minus 1 primes. So whatever n is, I have the first n minus 1 primes, and I'm tasked with computing the next prime after I have the first n minus 1 primes. What's that nth prime? If you already have the first n minus 1 primes, I'm going to store the n minus 1 primes in a list. I'm going to get the maximum value of that list. That's the highest known prime. Notably, I don't care about the order of the primes. The order is not defined here. But I'm going to get the max one, whatever that top one is. I'm not going to get the last element of the list or the first element of the list. I'm going to call it dot max, which is another Scala shorthand like we saw last time. It's going to reduce the list using the max method to get that max method. Or max prime. So I get the max prime. I'm going to call another recursive method where that's going to search for primes. It's going to check if I is a prime. Given a list of primes that are already known, if I is a prime, return it. If I is not a prime, check I plus 1. So I'm going to say find me the next prime, starting with max prime plus 1. And here are all my known primes. And append that to my known primes and then return that appended list. The find prime method is going to check is, and here's a fairly dense line, take all my known primes, fold left starting with false is my initial value, and combine all of these elements by checking, is I divisible by the element I'm looking at or the accumulator? So false or is I divisible by 2? If that's false, false or I divisible by 3, as we'll see later, and it's going to check, is this divisible by any of the known primes? If it's not divisible by any prime, so if that returns false, I'm not divisible by any known prime, then this must be a prime, and I can return it. Else, check the next number. If you don't see that all that works, you'll have to trust me. Well, at least for n equals 3, you're going to see that this absolutely works. But if you don't see it all, you have to trust me. This thing works. So let's jump to the middle of an execution of this where we've made it to our base case. So we call this with find n primes, first n primes of 3. N is 3. We don't hit our base cases. the first thing that we do is compute first n primes of 2, put that on the stack. That doesn't hit any base case. Find primes of 1, put that on the stack, and now we're at n equals 1, we're at our base case, and we have 3 recursive calls on the stack and our main method call on the stack. Here, we're going to create a new list with just the element 2 and put that on the heap. So we've allocated our heap space, we've got our first list. Lists are immutable, is of course the big punchline here. That list is never going to change once it's on the heap. That list at the reference 1 is always going to store just the value 2. That list can't change at all. So we've created a brand new list, and we're going to send this back up the recursion and start accumulating to this list, but we're going to do that by creating new lists, because lists are immutable. So we get our return reference of 1, we get that in the next recursive call. So we got this reference, that's going to be returned, and then this frame is going to resume execution. It's going to get that reference at 1. This is going to resolve to at 1. Get this list of 2. I'm going to store that in n minus 1 primes. We have this reference at 1 here. I'm going to call max on that list, which is just 2. So I get 2 as my max prime, and I reach my other recursive method. I'm going to call this other recursive method to be able to check for the next prime. My max prime is 2, so I'm going to call this with 3. And a reference to that list of all my known primes. So I'm going to pass this list by reference. This is something that we've seen before, passing this reference around our code. So we just have one list. We never make a copy of this list. Well, not yet anyway. We're just passing around the reference around our code through different recursive calls. Now we're going to check I. I is 3. Known primes is this list of 2. 3 is not divisible by 2. So we're going to return it. Hit our base case right away, nothing to check. We're going to return 3. We get this return value of 3, and this is where we finally get to see the immutability of lists in action. So we're going to prepend the value 3, find prime, that method call resolve to 3. We're going to prepend 3 to the list that by the reference at 1. So we go to at 1, and we're going to prepend 3, but we cannot change the lists because lists are immutable. Lists are immutable, so this is actually going to return a brand new list with that element prepended to it. So this call to prepend is going to create a brand new list with that element prepended to it and return a reference to that brand new list that was created. That's going to be the return value of this recursive call. So all this frame goes away and resolves to that reference at 2, referring to that new list that was created from the base case, and then prepending 3 to that base case list. This is our new list. This is what we're returning. But this list is still on the heap, and it remains unchanged. So this is going to return back to our other call, which was waiting for first n primes of 2 to return. Oh, I wanted this note somewhere, but I forgot where I put it. So if somewhere else in our program, so since this list is unchanged, if somewhere else in our program, some other code had a reference to this list, it does not matter what we do in our code, anywhere else in the entire program, we're never going to mess up that other code with that reference. They have a reference at 1. That list forever, for all eternity, until the program ends, is going to store the value, or it gets garbage collected, is going to store a list that has just the value 2. So no matter what we do, we cannot mess up any of our other code. Because we're using this immutable data structure, this immutability is not going to let us mess anything up, which of course, I mentioned it before, but is going to be very important when we have concurrency, when we have 2 pieces of code running at the same time, or At the same time, if they're both working with the same data structure and that data structure is mutable, or whatever object it is mutable, we're just asking for trouble there. But if it's immutable, we have no issues. We cannot mess that up because we cannot make changes to it. So this list is unchanged. This list, same thing. This is never, ever, ever, ever going to change. We cannot mess anybody up who has a reference to this list. We can't interfere with their computation because the list is immutable. All right, so this next recursive call gets that reference at 2, gets that list, a reference to the list that stores 3 and 2. It's going to resume its computation with that list. Max prime is now 3. We're going to call find prime of 4 and at 2. We hit our recursive step. I is 4. Since 4 is divisible by 2, we get true from this fold left. Not true is going to be false, so we're going to go to else. We're going to check the next prime. We're going to check 5. 5 is not divisible by 2, it's not divisible by 3. So we successfully found our next prime. We're going to return it. We're going to return that to that previous recursive call of find prime, which is going to return it back up to first n primes of 3. This gets that return value 5. Hits this line, find prime resolved to 5. We're going to prepend that to n minus 1 primes, which in this frame is storing the reference at 2. So we're going to go to this list, call prepend of 5 on that list. That's going to create a new list with 5 prepended to this current list, return a reference to that brand new list. Get this list, new list, which we'll say is stored at 3. And then we're going to return a reference to that new list that was created. So we're going to return a reference to that new list. Give that list to main. And main's going to be pretty happy because this reference that it finally ended up getting happens to have the first 3 primes. We didn't specify any order. I'm doing this from greatest to least, just the way I set it up. But it gets the first n primes just like it wanted, just like it expected. We're going to print 5, 3, and 2 to the console. So we ended up creating 3 lists. Every time we prepended to this list, we created a brand new one, which hopefully by now answers that question. If we have a list and we're adding a value to it, how come I can't just add a value to a list? How come I have to reassign it back to this list variable? This is why. It's because you're creating a brand new list every time you simulate a modification to that list. Adding an element, removing an element, doing anything to a list. Every time you're simulating a change, you're actually creating a brand new reference to a brand new list containing all the same elements, but with that change applied to it. And this is what we mean by immutability. These lists never, ever, ever change that are in the heap. Once they're created, that is what they are. They're never going to change any elements, but we can kind of simulate these changes by creating new lists with changes applied to them.